Hello and welcome to R for Civil Engineers, our Microcourse-I that focuses on programming concepts and numerical methods. In the last lecture, I provided you with an outline of this course, the topics that we are going to cover, as well as enumerated a set of student learning outcomes or things you should be able to do upon completion of this course. To kick things off, we're going to take a brief tour of computing in civil engineering over time. We'll look at the history of computing in civil engineering in order to motivate you to understand how we got to where we are today and why learning programming languages has become important again for civil engineers. So without further ado, let's jump right in and take a whirlwind tour of computing in civil engineering. It's not hard to understand that computing and civil engineering have had a very intimate relationship ever since its beginnings, because engineering, after all, is application of physical and natural principles using the language of mathematics to build society. So some techniques, such as the unit hydrograph, which is based on the superposition principle or the linear control theory, was actually put forth almost 100 years ago, and it still continues to be used today. When we want to study computing in civil engineering in a more formal fashion, it helps us if we can divide it into different eras. It divide our time period into different eras. So I'm calling the pre-1960s as the era of analytical solutions. I'm going to call the era from 60s to 80s as the era of mainframe computing, the 90s to 2010 as eras of Windows software and personal computers, and then 2010s to present, which is the last 10 years or so, as the modern day era where you're seeing cloud computing, generative AI, and the list continues. Analytical solutions or closed form solutions are exact mathematical functions. Simple example is if we have a quadratic equation, a quadratic algebraic equation, ax squared plus bx plus c, you can find the roots or solve for x using the quadratic formula, which is an analytical solution. Similarly, you can take some differential equations, some linear partial differential equations, and subject to appropriate initial and boundary conditions, you will be able to get some exact solutions. Here I show you the Bessel's function, a somewhat nasty looking ordinary differential equation, second order ordinary differential equation. It is nonlinear as well because of this x squared term. You can solve this problem and the solution results in what is known as a Bessel's integral or a Bessel's function that I show here. So these are some of the things that came out, or these are some of the things that came out during the era of analytical solutions. Civil engineers embraced analytical solutions and used them very creatively to build a lot of different things, to make a lot of advancements. Needless to say, the curriculum back in the 1960s and before had a lot more mathematics than what we have today in our curriculum. So civil engineers needed a very strong grounding in mathematics before they could take on studies in civil engineering and practice as civil engineers. 1960s, post-World War, even in 1950s, 1960s, saw advancements in computing. In particular, the discovery of transistor and as well as the solid state electronics led us to this mainframe computers or development of these mainframe computers. IBM was a market leader in making and selling these machines, and by 1970s most universities had at least one mainframe machine that they used for scientific computing. If you wanted to do scientific computing on a mainframe computer, you had to use a programming language called Fortran, which stood for formula translation. Civil engineers had to learn Fortran to perform calculations using these mainframe computers. So, needless to say, Fortran programming became part of undergraduate civil engineering curriculum, and typically, computer science departments offered a course in Fortran programming for engineers that civil engineers took and tried to use it in their coursework. Um, what came out during this era is that many modern day numerical techniques, have their genesis or origin in this era. This era of 1960s, 1970s also coincided with a lot of construction, large scale construction activity in civil engineering, particularly in the US, and several new techniques such as the finite element analysis and linear and nonlinear optimization and their applications to civil engineering problems. All of these started coming out during this era and continue to be used even today. By 1980s, early 1980s, personal computers came into the market. The idea was that you didn't need to have a mainframe computer to do your tasks. You could do a lot of that using a computer, a much smaller computer called a personal computer. And by late 80s, these computers had gained enough memory or had enough power that engineers started using them in there for engineering purposes. Right around this time, Microsoft launched its Windows. So in early 1990s, you started getting Windows 3, which was perhaps the most stable version of Windows. And PC computing, became more commonplace because of enhancements in the microprocessing chips. Okay? So many programs that were written in Fortran during the mainframe era got ported onto PCs, and graphical user interfaces were written to support running of these programs. Typically, these graphical user interfaces were written using a programming language called Visual Basic. So you had Fortran backend and a Visual Basic front end, so people could put in data, create the files that were needed for the Fortran program to run, which would run in the background. So the advantage of this was that modeling, computational civil engineering, computationally heavy civil engineering was no longer restricted to universities and research labs. Even practitioners, consultants, and others were able to run these models without needing large computers. And also, because you had graphical user interfaces, a lot of these programs could be run by people who were not formally trained in Fortran or formally trained in numerical methods. So, because this all of that became a black box and was kind of hidden from the front end, which the engineers interacted with. So as this started happening, programming started to take a backseat in civil engineering curriculum as well. Many schools in the late 90s downplayed the programming requirements. Many computer science departments stopped teaching Fortran. So civil engineers said, well, they don't really need to have a background in Fortran anymore. So they don't really need to learn C or C++. So we're going to teach some computing that's useful for us, say using MATLAB or Visual Basic or some other programming language that's readily available. And this idea continues in our curriculum even today in most places. So, so the upshot, it became available, or models became available to people who were otherwise non-programmers and not trained in numerical methods. The downshot is that computing itself was taking a backseat in civil engineering curriculum. So now coming to the modern computing era, this is era of the last 10 years or so. Internet, of course, has become very powerful and commonplace in the world. We no longer have individual mainframes, but we have computers on our desks that are more powerful than many of the mainframe computers in 1960s. But we also have what are known as very large distributed computing clusters or data warehouses. So this has given rise to cloud computing, which is taking the idea of mainframes and internet and connecting them together. So because of this, data has become a lot more easily accessible to civil engineers. And concomitantly, civil engineering sensing has also seen many advancements. So you're getting a lot of data in real time or in near real time that was simply not available, say, 10 plus years ago or so. So if you look at civil engineering and look at all these modern computational advancements, it becomes clear that you can do a lot more than what is possible with your discipline specific software or spreadsheets. But to do that, you need to learn new programming skills. Okay? So, modern programming tools are therefore becoming again essential for civil engineers. So, we probably will have to go back and train them a bit more in computations than we have done in the last decade or the last 2 decades. To help us with this process, we have several new and few open source and free tools such as R and Python. Although these have been around since 1990s, their use in engineering is gaining a lot of popularity, particularly in civil engineering. And of course, in November 2022, the generative AI, basically burst into the scene of our computational space. So now we have ChatGPT, Google, Microsoft Copilot, and Google Bard, and others that hold promise in helping us navigate both the computational methods, the data, and such. But still, it's a very emerging technology. So being able to use this techniques correctly is important if you want to learn programming tools in the future. So, to kind of summarize, we had the era of mainframe computing where computing resources were limited to a few places, universities, research labs, or very big organizations. Computing implied knowledge of Fortran and understanding of numerical methods. So, this is akin to fishing in a pond. A pond has a few fish, and you need to know how to fish to able to catch that fish and do something with it. Of course, you may not catch a very big fish because your pond is fairly small. The era of personal computing led to canned packages, and this is more a convenience oriented approach. Basically, you didn't have to fish because you were given a fish, although the fish you got was one type of fish, let's say tuna, and you had to get creative and do as many dishes as possible with that fish that you were given. The modern computing blends both of these worlds. So modern day software like R and Python provide access to numerical methods, so you can engage with numerical methods completely as a black box, use built-in functions or available code, available libraries, or as a white box where you can write everything from scratch. So this is more a knowledge-oriented, retains some of the convenience, but also requires you to do some work. There is also a wide range of platforms and open source data. So you're not restricted to just a few data structures, a few data types. So you have to be able to explore many different things, or you can explore many different things. So this is almost like you're now fishing in an open ocean, but you have some modern day tools to help you fish. You still have to know how to fish, but things are making it easier for you to fish and catch the type of fish that you want. So your creativity doesn't have to be in how many dishes can I cook with a tuna. I can now have access to tuna, salmon, halibut, and a wide range of other edible fish. So, in closing, you have seen that computational methods and civil engineering go hand in hand. They are very intimately tied. They have been so for hundreds of years. This is not something new. Many advancements that we have seen, particularly on the computational side, has happened during 60s and 70s or before. And what has really changed in the last 40 years or so is how we interact with these computational tools. So first we had to use Fortran to interact with computational tools. Then came PCs and spreadsheets and CAN packages that allowed you to interact with these tools almost in a black box manner, which also meant that you couldn't do a lot, but you could do some things and you could do it easily. What modern advancements are trying to do is kind of take you away from that and take you back to programming a little bit, but they are providing you with a lot of new tools and new techniques that makes programming easier. It is still accessible, so it is trying to retain the best of both worlds, the mainframe computing era as well as the PC computing era, and provide new set of tools and technologies for civil engineers to build better societies. So hopefully with this history, you have an understanding of the purpose of this course or how this course has evolved. In the next video, I'm going to talk about installing R in RStudio. We're going to make use of generative AI to do that. And then after that, we will jump into the core elements of our course, namely data structures and other concepts. So till then, take care. I will see you in the next video. Goodbye.